So really, just to kind of sum up the types of lenses we have, we can group them into two categories: lenses that are going to focus the light down, or converging lenses, and lenses that are going to spread the light out, or diverging lenses. Pretty much for everything that we are going to use in this class is going to be a double concave and double convex lenses. Just keep in mind there are other types of lenses that have very useful applications. However, they're a little bit more complicated than we'll touch upon in this class. If you're going to go into, say, eyeglass making or something like that, then what you're going to see is something that's called Lensmaker's equation. And what that really is going to do is it's going to relate the focal length to the index of refraction, and then the two radiuses of curvature of the two sides of the lens. So here we're going to have kind of one radius of curvature, that's the first surface, and then we're going to have this secondary radius of curvature. And we can also play with the material that our eyeglasses are made out of. Graphical method for lenses is going to be very important and very similar to what we did for mirrors. Essentially, it's very useful to know how to do this, so that way you can see if your calculations are reasonable. We're going to draw three principal rays. First, let's do a converging lens. We're going to have these three guys right here. I typically draw 1 and then 3 and then 2 is just kind of gravy. Number 1 is the ray that comes in parallel. We know it's coming in parallel, so it needs to go through the focal point. So it gets bent down through the focal point here. Then I draw the one where it goes through the focal point on this side. It's going to come out parallel. So the intersection of those two is going to be that point here. We can kind of see here that the image is going to be there. And then the last one, you just kind of cut through the center of the lens. It's going to pass through undeflected. And like I said, that's just kind of gravy. So here we have our object distance, and here we have our image distance. We still have the same standard equation: 1 over object distance plus 1 over image distance is going to be 1 divided by the focal length. So this is the equation we'd be using to go along with this. For a diverging lens, same type of deal. Start off with the one that goes parallel. It's going to get bent outwards, but it's going to be kind of pretending like it's coming from the focal point. So if I put an observer right there, they're going to observe an image as if it comes from the focal point. Number 3, we want to have the ray that's going to come out parallel. Well, it's going to come out as if it came from this point, this focal point right here. So kind of dash that guy, and we come back right here. And then of course we draw our one that goes right through the center and goes through undeflected. And here we have our virtual image right here. Much like with curved mirrors, object distance is going to kind of matter. Highly suggest you get yourself comfortable with drawing rays 1, 2, and 3. If we have an object that's outside of the focal point here, the image is going to be real and upside down on the other side. If we move the object closer to the focal point but still outside of the focal point, the image is still going to be real and further away. It's also going to be getting larger. You can kind of see that here. Move it even closer, it's going to be, image is going to be even further away and also even larger. If we put the object at the focal point, you can kind of see us drawing ray number 1 coming in parallel, coming out through the focal point. Draw ray 2 through the center of the lens. You can see that the image is actually going to be at infinity. If we move the object to inside of the focal point, trace out all of our things, the image is going to now be virtual, erect, and also larger than the object. So this is going to be kind of like a magnifying lens. So kind of something you'd see that's going to go in towards a microscope. We can also stack lenses together and make images of images. So following example 13.4, here we have an object, and we can draw kind of our ray coming in parallel, coming out through the focal length. And we draw our one coming through the focal length and coming out parallel. So here we're going to form some image. If we know the distance of separation from these guys right here, then what we can do is we can figure out how far, we need to figure out how far away this image is. We're going to then treat this image as the new object. We're going to draw our ray out parallel, coming through the focal length over here. and we draw our ray coming out through the focal point and coming out parallel, and we can form a new image. So that's going to be the image of the image. And what we would essentially do is we just simply apply this equation here twice. First for the first one, where we know the object distance is 12 centimeters. We don't know what the image distance is, and we know the focal length of the lens. In this case it's going to be 8. We can go ahead and solve for this guy right here and figure out that S prime is going to be 24 centimeters. That tells us that this distance right here must be 12 centimeters if we know the distance between them. So we can go ahead and say now our object is located at 12 centimeters. I'm interested in where my image is going to appear at, and I know the focal length is 6 centimeters. And so I can figure out that my new image is also going to be at 12 centimeters. Now this can become slightly complicated if these lenses are too close together and you have overlapping focal points, but don't worry about that for now. Now let's take a look at some real-life applications of stacking lenses together. If we take a look at just a very basic SLR camera, what we're going to have is we're going to have some object and we want to make some image on it on top of a CCD array. And what we do is we have a series of lenses, slightly more complicated here. And what we can do is we can adjust this distance in between them, therefore adjusting the magnification of the of this key right here. And it's also going to be passing through this little guy right here that I'll talk about on the next slide. So really being able to adjust that distance between the lenses is going to allow me to change my image distance and change my magnification. Now this guy right here, what that guy does is that guy lets in different amounts of light. It's going to be related to the F number, and essentially as we make that aperture smaller and smaller and smaller, we can we'll let less and less and less light in, and we can also make the picture very blurry in the background or very sharp. The eye is actually going to behave very similar to a camera, in that we're going to have some object. It's going to come in, it's going to enter the cornea right here, which is essentially going to start to focus it down, and then we're going to have a second lens right here with some muscle that can flex flex the lens a little bit, changing where the image is going to occur and how sharp the image is. That image is going to be picked up by photoreceptors that are on your retina. These photoreceptors are going to be in the form of rods or cones. Cones are going to give us color, and then rods are going to be the black and white, and also when we have low light. We know that if there's low light, we have, if we have low light, we typically see more in black and white than we do in color. And we also have a pupil which can get larger and smaller and let in different amounts of light, also changing whether the image is blurry or not. We can of course have some defects in our vision. If you want to just kind of picture a normal eye with parallel rays coming in, it turns out they're going to focus just on the retina, so it's going to be perfect. If we're nearsighted, it turns out that our eye is too long, and so the focus is going to be a little bit in front of the retina. If we're farsighted, the focal point is going to be behind the retina, and we can correct this with glasses, as I'll talk on the next slide. Keep in mind, however, that as we get older and older and older and older, this near point is going to get further and further and further away, which really means that we're going to have a harder time seeing objects that are close to us. We can of course correct for farsighted and nearsighted vision by using eyeglasses. If you consider just a farsighted eye, the object is going to be kind of behind the retina. What we do is we put a converging lens in there, and that's going to make the image appear as if it's closer. We're going to get a nice image that's focused on the retina now with our correcting lens. And lastly, if we were correcting for farsightedness required a converging lens, you could kind of convince yourself that for nearsightedness we're going to need a diverging lens that's going to make an object appear as if it's further away.